first, Josh is going to chat about the Minutes of Madness if you'd like to be part of it.
Sure. Yeah. So I was just going to say, you can think about it during lunch. If you have anything, I know of at least one presentation queued up for a Minute of Madness. If you want to use slides, you can maybe during lunch just get your slide loaded on the laptop. I mean, probably one or just a couple slides is all you would have time for typically. So I'd like to encourage people, if they have either a small result they just want to make people aware of, or a new idea you want to find other people interested in that topic, something like that. That's a good candidate for a Minute of Madness. That's it.
It starts now. So what I'm going to be talking about is a study we did using the WISP for activity recognition. And if you're interested in the paper itself, it was published at UBComp 2009, so you can find it. And there is done with a bunch of people from Intel and UW. So the basic idea is dense sensing with RFID sensors. So we take WISP and we put them on all kinds of everyday objects, and we can then get the accelerometer data back from the objects to tell which objects moved. And if we can tell what objects move in a pretty straightforward manner, we can tell what the person was doing. So if they use a toothbrush and a toothpaste, we can, decide that they probably were brushing their teeth. And there's applications in many different domains. The one that we're especially interested in is elder care. So we can tell if they were taking their medicine, whether they were eating, whether they were sleeping, how much water they were drinking. So what we did is we built the system. We had 25 WISPs attached to objects, 3 readers in the ceiling, had 10 subjects do to 14 different tasks. And we got 90% precision and recall for what activity they were doing. Like I said, if you're interested in the paper, look at it at my homepage.
Shane Clark, your minute begins now.
Okay, so I don't have any slides or anything interesting to say about my research, but I do have something I want to talk about really quickly. So looking at 2 papers that did roughly the same thing, Jeff and my own on solar-assisted WISPs, there's a real problem with the reads per second numbers we both reported, where I showed a max of 160 per second, and he showed a max of about 50. So I think people need to be careful to measure things consistently, and I would love to see someone come up with a good methodology for it, and at least for the sake of things like read rate. We actually have come up with something preliminary called the Franken WISP, which Ben will mention in his talk, but I don't have time.
Okay. So next up, Mike Burmester, and your minute begins now.
Now, okay. So this is madness. These are ideas. I thought about this some time ago. This is an important application. So you hide an object somewhere on the ground, bury it somewhere, and later on you want to find it. You put a tag to it, and you call it, and it'll respond to you, but to nobody else. So this is an important security application. Only the owner of that tag can trace the tag. And the adversary is very smart. The adversary can locate. You have a sort of triangulation. If that tag responds to anybody else, it will be immediately located by the adversary. So it will only respond to you. That's the application. Landmines I have in mind, but this is military applications and other such applications. It's very important. And it's very hard. It's not easy. I have one for the clocks. You can digitally sign a clock. You need very smart sort of tags which have okay.
Okay. Moving on. Madness. Dan Yeager is going to give his minutes, and he actually. Okay.
But slides, the title slide and the...
Okay, and that your minute has begun.
All right. I'm going to talk about some work that wasn't my work. It was done by Richa Prasad, a graduate of University of Washington Computer Science Department. So she was looking into trying to quantify the performance of WISPs and also develop some tools to troubleshoot them more effectively. And what she developed was a board that connects to the header pins of the WISP, and it actually uses the same microcontroller. and it has a RS-232 to USB converter. And so what this allows you to do is monitor signals from the WISP and send them to a computer via a USB cable. And so you can monitor the unregulated voltage and try to decide about the power consumption or just digital events. So you can talk to me afterwards about this. Thanks.
All right. All right. Next, Matt Trotter.
Okay, y'all. Backscatter cell phone right here. Imagine your cell phone without the battery, and you get the downlink from the cell tower, getting power and the downlink into your cell phone. You can listen to it, and when you talk, you modulate the load and analog using analog or with an ADC, and you send the uplink from reflections. So backscatter cell phone. I think you can test it using the WISP since it's so open-ended. You can attach some ADCs and some DACs to the WISP and test the idea out. Who knows? You might get some really fancy cell phones.
All right. Thank you.
With this stuff. So I think there's a lot of tribal knowledge and a lot of maybe misconceptions about what you're going to get out of the box. So this is kind of give you a heads up on what that would be. Okay. Okay, so we're a little bit of introduction. Talk about more of the analog front end and some of the details about how we're going to harvest energy, how we're going to communicate, what that means for the entire platform as far as power management, and then how that kind of hooks into MS-430 and what those responsibilities are. Later on, Michael Buettner is going to talk about the protocol, and Dan's going to talk about some firmware. We'll show some results and let's talk about a few sensors, and I got a little demo. So we kind of already identified, the major chunks here. RFID, we're transmitting power, we're transmitting data, or we're getting backscatter information back. That's all pretty well and good, and we have to kind of replicate that. So here's a WISP platform. I realize most of you have probably seen the demos, but it's probably useful just to show the hardware again, right? So about 3 meters of range, 2 meters of range. It really depends on what kind of multipath environment you're in, how well you're going to do. It's got this fully programmable MSP430 on it. So, we've open sourced this whole project. You guys can just start, in theory, just start whacking away with it and creating applications right away. We have onboard sensors, temperature sensor, 3D accelerometer. We can measure how much voltage you're getting off of it. So you can get a rough estimate of how far away you are from the reader, these sort of things. And certainly, we've broken out all these, we've got lots of header pins here. So there's ADCs available. If you want to go prototype another sensor in here, you just kind of solder it up and write the code for it and you're ready to go. We've got the real-time clock functionality. We have software-defined basically RFID tags. So a lot of the work that was done that was pretty difficult was actually getting the MSP430 to do the RFID protocol. So you can go and tweak that, right? So there's Michael Buettner did a software-defined RFID reader. Now we kind of have control over both sides. And I know there's some other people working on this. And again, we've open sourced this, and I think what's really interesting here is, there's a lot of ASIC work doing, but you can't really change that, and it's not really accessible to people. So now you don't have to be an integrated circuit designer to work on RFID. In fact, I'm really hoping we can get some artists and people who know nothing about technology using these things to do new and creative applications that, I'm never going to think of and never going to work on. So that's kind of my hope. So here's the general block diagram of the WISP. So certainly we have this antenna, impedance matching network. We're just doing a simple L match, right? And so on an integrated circuit, there's no discrete impedance matching network. We have this power harvesting block that's taking this RF energy, turning it to DC. There's power management block and the demodulator. So the demodulator is taking this AM modulated waveform and turning it into bits. There's a MSP430, and it has a bunch of nice built-in